Great. So welcome everybody to our usual seminar. It's a great pleasure today to have Jie Ma. So we know each other with Jie long time since he came to UCLA to be my postdoc. So it was really great times there. We did a lot of interesting work. And today he will give a talk on extremal problem on K-critical graphs. Please, Jie. One remark. So if you have questions, you either can unmute yourself or write it in the chat, and then I will read it for Jie. So you don't need to follow the chat, Jie. Just concentrate on your talk, please.
Okay, thank you, Benny, for the kind of invitation. It's nice. It's really great pleasure to give a talk at this event. Like Benny said, we have meet. Now, definitely more than 10 years ago, it was the year of 2011. I think when I come to USTC to be a postdoc under Benny's advisor. So it's a really great honor to have this opportunity to give this talk. So we're going to talk about extremal problems on K-critical graphs, and this is a joint work with some students at the USTC, where I now work for. So let's start with the definition of a K-critical graph. A graph is, we call it K-critical. That means the chromatic number of itself is K, but every proper subgraph has a smaller chromatic number. So in equivalent way to say it is by deleting every edge, the chromatic number of the subgraph will decrease. And this is an important concept in the development of the graph theory. It was introduced by Dirac in 1940s and in his dissertation. And the importance of this concept is that in graph theory, people study like graph coloring, people interested in chromatic number. And for any graph G with chromatic number at least K, it will contain the K-critical subgraph. And often we are studying like sufficient conditions. We are interested in the statement in the form like any graph G with chi equals K, what kind of subgraph it contains, or what kind of global information we can derive from this graph. And in this sense, it's very important to study K-critical graph because this is sufficient. And for now come to the characterization of K-critical graph. It's only known that the three critical graphs are odd cycles. This is if and only if statement. It would be nice to know any structural characterization for K-critical graphs for K at least 4. But this is kind of like an impossible task because one reason is that it's already NP hard to decide if a graph has chromatic number equals 3. I mean, it's a linear time to know if the chi is at least 3, but it's NP hard to tell if chi is equal to 3. And there are lots of open problems remaining, and some of them are just in the extremal flavor. And I think the reason I like this those kind of problem because this study is basically falling in line between extremal and the structure. And definitely there are lots of structure things involved, but there are very many nature-like questions in terms of the extremal side. Okay, let's first look at the general properties for a K-critical graph. There are not so many. So what we know is basically the following. G has no click cut, so that means it is a cut vertex set, and the cut vertex form a click. You cannot have, for example, you cannot have a 2 cut and the 2 vertices form an edge. And we also know the graph has minimum degree at least K-1. In fact, we know a little bit more. We know the graph is even K-1 edge connected. We also know the graph is 2 connected because if we have a cut vertex, then you can then you can basically have lots of components, and this is already contradiction to the definition, because you can just throw away one component and remain the same chromatic number.
Cut vertex is also a click cut, right? So so you already said, right? That...
Yeah. Sure. Yeah. For edge connectivity, it can be higher. It's K minus 1. And there's another nice things for the K-critical thing is that it tells more than a little bit more than two connectivity. If we have a two cut, say UV, then there's a nice structure theorem says that if we have a UV, then this two cut will divide the whole graph into two pieces, and then we have a two induced subgraphs. That's called the F1 and F2, and then we know that the union of the edge sets of those two graphs give us all the edges of G. Moreover, VF1 intersect VF2 only in those two versus UV. Other than that, and the F1, F2 has the following property. We don't know which one, but one falling in one category. That is, if we add the new edge UV to say F1, then this new graph becomes a K-critical graph. For the other one, if we contract UV into a new vertex, then this is also K-critical graph. And basically, this structure thing tells us that we can view a K-critical graph as almost a three-connected graph. Okay, if you know, of course, in real three-connected graphs, there's no two cut. But in this scenario, if we have a two cut, then we have this structure. We can kind of do induction. We can go to smaller pieces and they just keep doing this. There are many solutions of conjectures in terms of K-critical graph relies on this information lemma. Okay. So, and it's very important to know actually the general construction for critical graphs. And again, there's not so many general construction we know. Here we just like mentioned three of them. The first one is the Dirac construction. So if we have a K-critical G1 and we have a critical G2, then when we look at the complete join of G1 and G2, this is a K+1 critical graph. There are other two, the highest construction and the Minkowski construction. For the highest construction, basically we just build smaller K uniform K critical graph to a bigger K critical graphs. And here the picture indicated this construction. So if we take a G1, take a G2, and take an edge in G1 and take another edge in G2, then delete both of them and identify a vertex and put a new edge. And it's easy to see that this graph is also K-critical. The Minkowski construction tells us that so if we are given a graph G, then we take example G. Here is a C5. Take a G and then copy the vertex set. And then let's call it V1 to V5, and here's U1 to U5. If in the original graph, U1, U2 are adjacent, now I will put the edges between U1 and V2, also put the edge between V1 and U2. And then I add an extra new vertex called W. This W is adjacent to all of these verses in the new copy. And then we can show that if the original graph is K-critical, the new graph is K+1 critical. Okay, so that's basically what we know for the construction. There's some other special construction to form K-critical graphs. Okay, now I want to just mention several interesting results in terms of this topic. The first one I want to mention is result of Toft. So Toft proved that in 74, he proved that in any K-critical graph G and fix any edges U, say E and F, then one can always find a K-1 critical subgraph which contains the first edge, but not contains the second edge. So this kind of tells us that there are many k-1 critical subgraphs. The second one study the minimum number of edges in a k-critical graph. The result of Postdoctoral and Tianchi, he proved that if k is 4, then the number of edges will be at least 5 over 3 times n minus 2/3, and this is tight. That infinity many 4 critical graphs can achieve this inequality. And there's another result due to Postdoctoral and Benny and this charter in 2017. So they proved that suppose the graph is triangle free, and we don't necessarily to assume it's k-critical, but say the chromatic number is equal to k, then such graph contains k squared times log k many cycles. Moreover, those cycle lengths are consecutive. Namely, if it begin with say t, then it's t plus 1, t plus 2, and keep going. Okay, so from those results, we see a typical statement that is we want to study say any k-critical graph should contain something. Okay, this something means sometimes it's just some special form of subgraph. Sometimes it's a general property. Okay. The many interesting like I mentioned problems.
Excuse me.
Yeah.
Could you go back to the last page? Like, what if this graph is not triangle free? Why doesn't
so thanks for the question. If it's not triangle free, then you can take a KK. So the click on K versus is a K critical graph. Therefore, it's not that interesting because there are only K minus 3 consecutive cycles. Actually, this result can be generalized in the paper. They can generalize like not only for triangle free, but also for if you put on Girth condition. If the Girth is say t, then here you expect that this should be k to the t. I think if I remember correctly. Yeah, this is the method of this can be generalized to a more general theory.
Okay, thank you.
Okay. So let's just mention some natural problems. So it's very natural to study the number of edges in minimal or maximal. It's also very natural to study say the longest cycle. And what is the size? What is the largest size of a say k-1 critical subgraph? In general, we can study any L critical subgraph where L is between 3 and k-1. And we also can ask if there are many, then how many of those subgraphs? But in later we're gonna see basically many of those problems are still widely open. This is an area which is underdeveloped. So now let's just look at I think the most interesting question and extreme problems in terms of k-critical graphs. And this is also if we read the literature, it's also the first problems from k-critical graphs. The Dirac mentioned this problem, mentioned the concept of k-critical graphs to Erdős, and the Erdős's like a first reaction is to ask what is the maximum number of edges. So we defined the maximum number of edges in an n-vertex k-critical graph to be fkn. And the first result comes from 70s by Toft. So he proved that because we know what is when k is 3, so in the remaining talks we're gonna always assume k is at least 4. Toft proved that when k is at least 4, then this function is in the order of the quadratic order. It's always some constant times n squared. And the most interesting case is when k is 4 and 5, and in those cases we know the constant is C4 is at least 1/16, C5 is at least 4/31. This is still the standing record for the bound. So let's look at the construction of top give. Here, so k is 4, and then we partition the vertex set into 4 parts. So here you see this is auto cycle C2k plus 1. Then we have independent set. We have a second independent set. Then we have another auto cycle C2k plus 1. And then we put a perfect matching between the first auto cycle and the first independent set. And then we also put a perfect matching between the second independent set and the second auto cycle. Between the 2 independent sets, we put a complete biparallelogram. Okay, so it's very easy to check that this graph indeed is 4 critical, and as we see, this graph has basically n/4 times n/4 many edges, which is n²/16. And this construction can be generalized. So to be more precise, basically here in the right picture you see n. So you can think m is half k. M is half k. So here we have m plus 1 complete. So we have a complete m plus 1 apartheid graph, and except one part. For all of those parts, we're gonna basically put a perfect matching between the part and a new graph, which is k minus 1 critical graph. Okay, so here is like our m is 1, right? So we have 2 parts, and for each of the 2 parts we put a three critical graph, which is auto cycle, and put a perfect matching. But in general, you can just do this. The so defined graph will be k critical. Therefore, then we can just say when k is 5, then we can just do optimization problems like recursively. So those will be 4 critical, right? So basically, you can write a recursion, and when you optimize, you get assuming the best bound for 4 critical is 1/16, then you get this bound is 4/31. Okay. But the game changes if k is at least 6. There's another family of construction which beat this construction when k is at least 6. The construction basically is simpler. It's just just take an example. Say k is 3q. The example is just taking the join of q auto cycles, because it's obvious. Basically, it's just generalization of direct construction, and it's kind of obvious to say this is a 3q critical graph. Then this tells us that fkn will be at least the number of edges in a Turing graph, the q-partite Turing graph. And if we factor out, we'll see this number of edges is equal to half minus 3/2k times n squared. In particular, it tells us that if k is 6, then q is 2, then it gives us a lower bound is n²/16. Oh, sorry, it should be, it's a typo, sorry. It should be n²/4 plus it. Because the construction will be just a join of 2 auto cycles, each of size half. So it's n²/4. Now if k is not modular 3, say it's the radius is 1 or 2, then basically it's the same construction, and we can get this. Okay, so that's just a matter of this constant delta k, but it's a constant. Okay. And then in the year of 2013, where Piggins find the new construction, And in his construction, basically he mainly interested in triangle-free K critical graphs. So what he gives is for K is equals to the same bound is 1/16 times n squared, but we need to minus a error term. When K is 5, interestingly, he also gets 4/31. And when K is at least 6, he got 1/4 times n squared. Now notice that this bound is tight because we're talking about a triangle free. So mental theorem tells us that triangle free, the maximum number of edges is just 1/4 times n squared. So this is tight. And for where Pickens constructing, basically it's like you utilize this idea. So instead of put a matching, he put something like other things. That's basically the for the lower bound of the maximum number of edges. Now for the upper bounds, that's a quite trivial upper bound. Assume n is strictly bigger than k, then we know in such n-vertex K critical graph, there's no clique size of k. So such graph is kk free. Therefore, the maximum number of edges is no more than the k-1 partite Turan graphs by Turan's theorem. Then Stibitz in 1987, he improved this. He proved that FKN is just like one step further. This is strictly less than the number of edges in an n-1 part Turan graph when n is big. And here is his proof. He is using the characterization of a Greenwell and the Loas for all subgraphs of K critical subgraphs. So what I mean is I defined a family of graphs. This family graph contains all subgraphs of all K critical graphs. Okay, and then they give a structural characterization for this family. And then using this this information together with the theorem of Simonovich, and this theorem actually is the Turan type theorem for the color critical graph. And because we can show that there is no in any K critical graph, there's no this graph. So T plus K-1 3K. So the plus means I can add a single edge in the Turan number in the Turan graph in the K-1 part Turan graph 3K verses. The reason is that due to this characterization, there should be no such graph. Okay, but on the other hand, this graph is color critical. So the chromatic number of this is actually K-1. So if we've forbidden this, then we get this bound. Okay, that's the original proof. There's another proof. I think this is much easier. The other proof relies on the information that any n-vertex K critical graph G only contains linear many K-1 cliques, and this is not trivial result. I'm gonna mention this later. This is proved by using some linear algebra method. But if we assume this, then as you see, we can just delete at most n edges. The graph becomes KK-1 free. So then we get the upper bound is this plus maybe plus n. Okay, but the advance of this new proof is that it works for any n. the Stibitz proof only works for sufficient large n. But for this proof, you can do for any n. But we pay a small price, say we add a linear term. Okay. Now let's pay a special attention to the case when k is 4. The low bound and upper bound tell us that there's a huge gap. It's 1/16. On the other hand, the upper bound is 1/4. So basically, that's the status for the past 30 years. So I find this problem and find this is ridiculous. There must be something can be done. That's why we study this. So it turns out we are able to improve the Stibitz result by a little bit. So when k is at least 4 and is large, we can improve the bound by a term of n squared over k squared. So at least tell us that the k minus 1 part Turing graph, this is not extremal. This is not the extremal graphs. And in fact, I think this is far from the extremal graph. Okay, and then when k is 4, we also we refine our proof and we can get a bound is no more than 0.164 n squared. Okay, so I want to emphasize our key lemma. I think this is a new, for me, this is tell us something information for a general k critical graph. So let's just look at the pictures. Assuming we have a k minus 3 clicks, so call it x1, x2 to xk minus 3. And then we have another vertex u, okay? And then we have a set w. The w is a set of common neighbors of those k minus 2 vertices. So as we see here, you can view this in the w, and those k minus 2 vertices between them is completely joined. Okay. Now, given this, we are able to say there's another set of a new set w prime, and between w and w prime, basically there is an induced matching. And if w is at least 3, then we also know w, this set itself, is the independent set, and there's no common versus between w prime and w. Okay, basically this picture. So if you recall the construction, the top construction for 4 critical graphs, you will find actually this induced matching thing is familiar, familiar, right? Because recall what is the construction. This is, you partition the vertex set into 4 pieces. The first one and the last one, those are order cycles. And the second one and the third one is independent set, and between this is a complete bipolar graph. But between the order cycle and the independent set, it's a matching. So in the so far dentist 4 critical examples, we do see a large induced matching.
Sorry, can I ask a question?
Yes, please.
So here you said the condition is the graph has such a copy, and also there's a set in those common neighborhood. But why don't you just pick W to be everything?
Why? No, W is the where
like
W
W
has
is
to,
a subset of.
Yeah, and in the proof, this is very important. Every vertex in W should adjacent to all of those k minus 2 vertices.
Yeah, I meant why don't you always pick W to be exactly the neighborhood of x1 joint with the neighborhood of
Sure,
X.
yeah, you're right. Yeah. Sure, I can make it equal, yeah. But this is more, you know, I mean, in the proof, actually, we take a subset. Yeah, but you are right. You can take just to be equal, yeah. In the proof, in the actual proof for our result, we're gonna take a subset. But yeah, so next I want to give actually proof of this. The proof of this is not it's not very long, not very complicated, and use the definition of a G being a k-critical graph. So here is the proof. So we take any vertex W, and this W again is adjacent to the clique and the vertex U. Okay, so I can delete the edge between W and U. I'm gonna consider G minus W. Okay, now by the definition of k-critical graphs, G minus WU is k minus 1. The chromatic number of this graph is k minus 1. Then we can partition the vertex set into k minus 1 independent sets, like this. I call it V1, V2, Vk minus 1. Okay, now I want to consider where those vertices xi locate in those sets. They form a k minus 3 clique. Of course, each of them will set in a different part. So let's assume x1 is in V1, x2 is in V2, and xk minus 3 is in Vk minus 3. Okay, now where those vertices W and U? Well, W and U must be in the same part. That's basically because otherwise, if W and U are in different parts, then you just add back this edge, right? Then it means the original graph G also is k minus 1 colorable. So cannot be the case. W and U must be in the same part. Okay, but this part must be different from the previous k minus 3. Simple reason, because W is adjacent to all of those xi. So W is adjacent to all of those xi. So let's assume WU is in the set Vk minus 2. Okay, now we see this. Very good. Let's consider the vertices in W minus W, like this. The set of W, delete the vertex W. Okay. Where possibly those vertices can lie. Again, those vertices is adjacent to the clique. Moreover, those vertices is adjacent to U, right? So this enforces us to say that W minus W must be in the last part. Okay, those vertices must be in the last part. Now this already tells us that this is the independent set. Okay. Moreover, the vertex W must have a neighbor in V minus K. Why? Otherwise, I can just remove W to this part. Then it tells us that the original graph G is K minus 1 colorable. So, okay, this is impossible. So let's assume this the neighbor of W called W prime. Okay. Now that this W prime is basically giving us the edge in the matching. This is W prime. W prime is distinct from the set W, and this argument works for all vertex W, right? So for all of those vertices, we can find basically like a neighbor, and we get the matching. This matching technically is not induced because we don't know the adjacencies inside of this W prime. What we know is in this bipartite graph is induced inside of this W, this is independent, but inside of this W prime, maybe there are some local things. Okay. So that's the proof of the key lemma. What does this key lemma tell us? It tells us at least one thing is the K critical graph, assuming there is a K minus 3 clique, then this K critical graph is far away from the K minus 2 partite Turing graph. Because in any Turing graph, we are not able to see a large matching, right? But here there is a large matching. So in principle, this already tells us that this bound cannot be tight. That's indeed basically how we managed to prove this together with the stability. We use Faraday stability. So if G is K R plus 1 free and the number of edges differ from the R partite Turing graph by T, here T is arbitrary number, not necessarily say epsilon times n squared, but any. Then we can find a complete R partite graph K, and compared with this K, the missing edges of G is no more than 2 times T. Now, having those two lemmas, we can give a sketch. So assume this K critical graph has at least E of TK minus 1 minus CK n squared many edges. By using Faraday's lemma, stability lemma, we can basically compare G with a complete K minus 1 partite graph. Then by using average, because we know there are many edges, right? They're much bigger than E of T K minus 3 and many edges. So by averaging, there is a K minus 3 clique. Then we can just take find those clique and find the vertex U and define the W. W is basically very close to one of the paths. Using the lemma, we are able to find another set W prime. Now at this stage, we already win because this W prime is disjoint from W and all previous V1 to VK minus 2. There are just too many edges. There are just too many verses. It's just already exceed n. So this is a contradiction. For the case when K is 4, actually we can do better because instead of using Faraday stability, we just take a typical C4. Take a typical C4, and then we look at the local structure around those 4 verses. But the thing is, one technical thing we are not able to overcome is here. So suppose now we have a large complete bipartite graph. This is W, and say this is another set. It's also huge, right? So principally, we can do both sides, right? From W, we can have a W prime, and from this side, we can have another matching. But the thing is, we are not able to prove that the set W prime and the new set, they are disjoint from each other. From top construction, we know they are disjoint, but we are just lack of some new arguments to say those two parts are disjoint. If there is a way to say that there must be disjoint, then I think we can improve the number of edges a lot. Okay, open province. So right now we know F4 is no more than 0.164, and the lower bound of F5 is 4/13.1, so that's 0.129. So I think it's been very nice to prove F4 is less than 4/31. If so, then we know F4 is smaller than F5. I mean, currently for K-critical graphs, we know our knowledge is very poor. We don't even know this inequality. But if you think if K is going up, right, the number of edges must be going up. But we don't know from any theory of this. That's I think if next step will be trying to prove something like this, improve the upper bound. There are other interesting questions. For example, if F6 is just equal to the lower bound, n squared over 4 plus n, Jason and the top conjecture that they believe this is not. So that says F6 should be strictly bigger than this equation. And another interesting question is that
Jay, when you say strictly bigger, you mean the constant in front of n squared over 4 bigger, or just the error term you want to include?
Even the error term we don't know. Yeah, even improve.
But what do you believe? What do you believe here? That's what.
I think even improve the error term will be nice. Yeah. Actually, it's debatable. So this is a good question. I don't know the precise meaning when Jensen and Toft when they conjecture this is not. Yeah. But the current record is that for F6, this even counting the error term, this is the best bound. Like, we don't know if this can be improved to say plus n plus 2. We don't know. Okay. Another interesting question will be if the limit of fkn divided by n squared, if this limit exists or not. That's for the I think I need to speed up. So that's for the maximum number of edges. In 1984, Gallet asked another question. Because one of the, if we remember, one of the top, like I mentioned, the top results say for any edges, any two edges, E and F, we can always find a K-1 critical subgraph contains the first edge, but not contains the second edge. So this tells us that there should be many K-1 critical subgraphs. Gallet asked if there are at least n distinct K-1 critical subgraphs. If this is true, then it's tight because KK. And when K is at least 3, it's trivial. So we concentrate on K at least 4. And let's from now on, let's define the GSG means the number of S critical subgraph in the graph G. So the question will be equivalent to say if the function GK-1 is at least n. What we know, the first result is due to Stibitz. He proved that this function is at least log n. So at least it means that when n going to infinity, this function will be going to infinity. Then the Albert and the Zhou result tell us that this function will be a polynomial. It's at least n to the 1 over k-1. And with Tianchi Yang, we managed to improve this. So we proved that this gk-1 function is at least n to the power 1 over k-2. So here is the proof. The proof is just needs a few lines. So the thing is, take edge and delete it. And just we play the previous, like when we prove the key lemma, the same trick. G minus E will have a K minus 1 proper carry. So it has a K minus 1 color class. Let's assume the two verses from E is in A1, okay? Then when we delete, say, the A2, G delete A2, the prime number is still K minus 1. So G minus A2 will contain a K minus 1 critical subgraphs. And this subgraph is defined from the edge E. So let's call it GIE. Then we put all those graphs in a list. This is called LE, G2 to GK minus 1. What we know for those graphs, each of them is K minus 1 critical. Each of them contains the edge E for sure. And moreover, for any edge other than E, they are one of the graph in the list not containing F. Well, why we want to mention this property? Because this property tells us that the list LE for every edge E are distinct from each other. Okay, so for each edge E, it has a distinct list LE. And this just tells us that the GK minus 1 function choose K minus 1, that will be the that will be the upper bound of the number of lists, right? In total, we have GK many, and we take like this list only consists of K minus 1 graphs. This will be the upper bound of the number of lists, but the number of lists is at least the number of edges. So we get the bound. The GK minus 1 is e to the 1 over K minus 1, which is n to the 1 over K minus 2. And then now let's focus on the case when K is 4. In case K is 4, we are interested in counting 3 critical subgraphs. That is the order cycles. So just let's define the GG to be the number of order cycles. There's a result of here. He proved that basically GG is at least 8n over 3. So let's say he answers Galet's question when K is 4. But this is not tight. We are able to show that for 4 critical graphs, the answer should be n squared. And n squared is tight because when we look at all the whales, that is the drawing of an order cycle with a vertex. It's 4 critical, and it contains n squared many order cycles. And our proof actually tells us a little bit more. But for the moment, let's turn our attention to another question. It's a question of Nestor and Rodo. They study the size of K minus 1 critical subgraphs. So they ask if there is a large subgraph. By large, I mean if n going to infinity, the size going to infinity. And for this question, it's only known when K is 4, because when K is 4, we know we are looking for order cycles, and that's easy. But when K is at least 5, we are, because there's no construction, there's no characterization for such critical subgraphs, so we don't know what we are looking for, and that's basically the difficulties. Okay, but if we are interested in finding large order cycles, then there are many results unknown. For example, the order result of Kelly gave us the first bound going to infinity, and a nice result of Noga, Alon, Krylevich, and Simon tell us that this is at least square root log n. And Asaf Shapira and Robbie Thomas improve this. The bound is tell us the bound should be log n, and this is tight. This is matched with the construction of Galet. Okay, but this is for the only for the order cycles. Okay, basically that's the only thing we know how to find, how to count in K-critical graphs. So I just quickly mentioned some of the proof ideas. So actually we prove something stronger. We prove something, so we introduce another parameter called TG. TG counts the number of years in a year decomposition of a graph G. And we actually prove that the bound should be T squared. Okay, skip. The same proof also works. We counting all the cycles, but the same proof also works for counting even cycles. For even cycles, again, the bound should be T squared. So back to the original question of Gallet, it's still open if when K is at least 5, GK minus 1, if GK minus 1 is at least n or not. But I think the actual answer should be n to the K minus 3 by extending the order wheel example. So I think I'm just run out of my time, but I prepared another topic as the counting the K minus one clicks in K critical graphs. If we think about K minus 1 click is just a special K minus 1 critical subgraphs, right? So in the previous problem, we want to find many K minus 1 critical subgraphs. But there's a dual problem. So we want to show that actually there's not too many K minus 1 clicks. This question of Gallet, he conjectured the number of K minus 1 clicks should be no more than the number of verses. And this is first proved by Stipitz when K is 4. He used linear algebra. And he also proved that it only makes sense to ask the question for K minus 1 clicks. If we ask for L clicks where L is smaller than K minus 1, then he gave us the construction, the answer should be n to the L, not linearly n. Okay, and this is solved by Albert and Zhou. They basically answer the question for general K, but then there is a new question. They want to tighten the bound. The conjecture this should be no more than n minus K plus 3, and they provide an example. That's the generalization of the order wheel. Okay, I skip, and then in a recent work of with my student Jun Gao, we prove this. Indeed, we can tighten the upper bound to be n minus K plus 3, and we only use linear algebra. So I think I just stop here. Thank you.
Thank you, Jay. It's really interesting talk and interesting questions. So any questions to Jay? So basically to understand, so there were some nice problems. So one was this problem of TAT, not Gallet, right? So, which says that I just look on K critical graph, I allow to delete some vertices, right? We want every time we want to delete some vertices to get, right, a different subgraph, which is K minus 1 critical.
Yes.
Right.
Yes.
And you believe that the linear bound is not true. So you should get better upper bound as well. You don't believe your bound is correct, but you believe also that both bounds can be improved.
So I believe he asked for if this is at least n, but even this is not known. Even this is not known for K at least 5. But I think something stronger should is the real answer. It should be at least n squared and above.
No, Jay, not this question. So the previous, right?
Yeah.
Like where you were
G, for the function G.
For the function G, right? So for the function G, you proved this. Yes. Stop it here. So you proved this n to the power 1 over k
this one.
minus 2.
Yeah.
If we believe n, but you say you don't believe n is true.
Yeah. I believe something stronger is true.
I see.
But, but right now we are just far from there. This is the best general bound. We only know n to the 1 over k minus 2. Take example, if k is 4, from here we only know square root n, right? But actually, if n is 4, we know from another result we know it should be n squared. Like from this. When k is 4, from the general result we only know square root n, but from this result it should be n squared. That's when k is 4. When k is bigger than 4, much less we know. We only know this. Yeah.
But okay, now I understand. So his conjecture was modest. He said n, but you believe that actually much more than n should be true. So we're really far from proving it.
Yes.
Yeah.
Yes.
He said n.
His question
But
just
you believe that it's actually almost n to the k minus something.
n minus 3.
I see.
No, n minus 2. Yeah, because when k is 4 is n squared. It should be n to the k minus 2.
I see. Oh. Interesting.
Because this thing is tricky. I mean, in principle, you can find many canonical graphs, right? Just keep deleting verses. But the thing is how to tell those are distinct from each other.
No, I understand.
Yeah.
I understand. Very interesting. Okay. More questions? So if not, so again, thanks Jay for very interesting talk. So there are lots of inspiring problems. People very welcome to solve them and send Jay solutions.
So nice.
we have one more talk this semester. It would be next week. So the concluding talk would be given by Alexei Pokrovsky. So his title and abstract is online, and I hope to see all you next week for the last talk. Thank you, Jay, again.
Thank you, Benny. Bye-bye.
Bye-bye.